So let's continue with chapter 10 on the radical reactions. And here we're going to look at thermodynamic considerations, the selectivity of halogenation, and stereochemistry of halogenation, and these are all halogenations of alkanes. So first, remember that we're going to look at the thermodynamics, and remember that delta G equals an enthalpy term, the delta H, plus an entropy term, minus T delta S. But here, the entropy term is going to be negligible because you're going to have two reactants going to two products. And so the entropy difference can just be ignored. We have two molecules going to two molecules. And so we're just going to have to look at the entropy, the delta H, and that means bond dissociation energies. And so this is a little table of bond dissociation energies, and this is only of the relevant bonds because here we're considering halogenation of methane. And so you can estimate the value of delta H if you look at the bond dissociation energies for the bonds broken versus the bonds formed. And so here, this is CH. Here, this is a column for the values of CH when you are using different halogens. And so, of course, these will be the same. This will be the same in all four reactions. Here we've got the dihalogen. And so this corresponds to the bond dissociation energies for the dihalogen when the halogens are these four different atoms. And now here we've got the halomethane. And so here once again halomethane in this column. And these values correspond to the values when you are using those different halogens. And then here you've got a hydrogen halide, and here's the column for the BDEs of the hydrogen halides when you have those four different halogens. And something that is significant that you can make note of right away is the rather high value of the BDE for the CH bond. It's 435, and it's higher than most of the values, all except this one for the HX corresponding to fluorine. So this is going to have a huge impact on the reactions. And what you're going to see as we go through all of this is you're going to see that the abstraction of H dot from methane is going to be the rate determining step. And that's because of the contribution of the bond dissociation energy of this bond in the reactions. So what we're going to have to consider in calculating the delta H in each one of these reactions, and I'm saying each one because we've got four different reactions here, and it's going to be the bond dissociation energies of the reactants. That's going to be something from this column, depending on whether we're looking at fluorine, chlorine, bromine, or iodine up here, minus the bond dissociation energies of the molecules in these columns. So if we pick X equals chlorine, you're going to use these two added together minus the sum of these two added together. And that's going to be the way you're going to calculate it. The bond dissociation energies of the reactants minus the BDEs of the products. And that's what you're going to see. So that's what's calculated here using the values from this table. And so it's shown here for you. This is the exact same reaction that you saw on the previous slide. And so here you can see that here you have the methane, where the bond association energy, the carbon and hydrogen bond, is not going to change. And here, this tells you which halogen you have in the reaction. And so using the BDEs of the CH bond and the XX bond in each one of these, sum those together and subtract the sum of these two, and you will get this as the delta H. And one thing to notice in the comparison here is that this is extremely exothermic. It is so highly exothermic that it's difficult to control this reaction. And sometimes reactions involving fluorine just go with such force that they're almost explosive. And so in those cases, they are not very valuable synthetically, because when you have something reacting that fast, it will just, react with the first molecule that it comes in contact with. And so remember that the reactivity is inverse to the selectivity. The more reactive something, the molecule is, the less selective it will be. And that's because it will just react with whatever it bumps into first. So it becomes a totally statistical thing. Chlorine and bromine are much more reasonable. They proceed exothermically, but with very reasonable numbers. The iodination is endothermic, and so it's not very useful. And so in a lot of cases in our discussions, you're just going to see us use chlorination and bromination to discuss, because those are the most useful. So this has just, this states what I just explained to you, except it's on a different slide. So now let's look at chlorination and bromination. So this is breaking it down into the first step, the first propagation step, and the second propagation step. So this is telling you that this is going to be downhill, energetically downhill. It's going to be exothermic a little bit, and here this is going to be greatly exothermic in comparison. The second step is much more exothermic than the first one. And taken together, the net reaction, it is a very exothermic reaction for chlorination. Bromination, which is in this column, notice that the first step is endothermic, but the second step is exothermic enough to give you an overall exothermic reaction. And what this is going to do is it's going to make bromination, since it's much less exothermic and the first step is endothermic, it's going to make bromination a much more selective reaction and much more useful synthetically. And that's what you're going to see here. So this is a way of drawing what I just said on an energy diagram. Here you have reaction coordinate and potential energy, of course, and this is chlorination. And you can see the first step, you have a small energy of activation, and it is somewhat exothermic, and so you're going downhill somewhat, and then the second step goes downhill a lot more. And overall, of course, the reaction is exothermic. And so this reaction is not going to be extremely selective because it's very reactive. This reaction is very reactive. Now, bromination, on the other hand, you go uphill in energy over a huge energy hill, a large energy of activation. And so remember, the first step is endothermic, and then you have a smaller energy hill going way down, and so overall you have an exothermic reaction. And so the heat that's generated in the second step is enough to keep the reaction going, as a radical chain reaction. And so here we have, since you have a large energy of activation, this reaction, the bromination reaction, is much more selective. That means it does not simply react with the first thing it bumps into. It has just enough energy to get over this large energy hill. And so it's going to take the lowest energy pathway. Over here with chlorination, since the energy hill is not so high and it's got a lot of heat generated in it, it's going to be less selective, and it doesn't necessarily have to take the very lowest energy pathway. Okay, and you're going to see that reflected in some of the products that are generated. You're going to see a difference here in the selectivity of the products, and it's because of the reactivity here compared to the reactivity here. This is less reactive, more reactive, less selective, more selective. Now, so this is what is meant by the regioselectivity. This is how it's going to manifest itself. So let's look at substrates that are more complex than, say, methane or ethane, where you've got a possibility of different types of carbon. So here, this is a primary carbon, secondary carbon, primary carbon. And the statistical effect is going to be of these different types of protons is you've got 6 protons that are on primary carbons and 2 on a secondary carbon. So it's a 3-to-1 ratio. 6 to 2, 3 to 1. So you've got 2 different products that are possible. You could get chlorination or bromination at the secondary carbon, or you could get substitution at the primary carbon. And you remember which one has the more stable radical center formed. The secondary carbon is going to give you the more stable radical, and the primary is going to be less stable, just like in carbocations. So now let's go on with the reaction and look at the results of this. So here we have the chlorination reaction. Remember, the one that I said is not so selective. And this is just the first step. This is the hydrogen abstraction step of this reaction. So the hydrogen abstraction takes place, and then there's another step, which is the radical abstracts chlorine from Cl2. So there's another step down here, which is not shown. This is just the first step of this reaction. And why do we just need to consider the first step? Because when the H dot is abstracted, that's going to create the radical center. And wherever the radical center is created, that's where chlorine is going to go. Because you're not going to create a radical center up here and then have chlorine attach at the terminal carbon. Wherever the radical center is created, that's where you're going to have substitution. And so this first step is the only step that we need to consider in the regiochemistry. So here, this is the step in which the Cl dot from the initiator abstracts a proton. So Cl dot will come in and abstract, Cl dot will abstract H dot. It will abstract a hydrogen atom, not a proton. So it will abstract a hydrogen atom from here or from here. And so if it abstracts a hydrogen atom from the terminal position, it's going to give you a primary radical, and it will go over this red pathway. If the Cl dot from the initiator abstracts H dot from the secondary position, it will give you a secondary radical. Okay, and once the primary radical or the secondary radical is formed, that is what abstracts Cl dot from the reactant. Okay, and that has determined the regioselectivity. So this is the step where the regioselectivity is determined, and we don't need to consider the second step. The second step is out here, but we don't need to consider it because it has nothing to do with the regiochemistry. This is what determines the regiochemistry. And so you can see that the primary radical is higher in energy than the secondary radical, which is the exact same for carbocations and for the same reason, and you already know that. And so you can see that the transition state leading to the primary radical is higher in energy because the primary radical is higher in energy. And you already knew this. This is what you typically see. The transition state leading to the secondary radical is higher in energy, is lower in energy, just like the secondary radical is lower in energy. And so that tells you the relationships of the transition states, and that tells you how much energy of activation is required to get to each one. There's a higher energy hill to get to the primary radical than there is to get to the secondary radical. But you would have already known that because this is analogous to the reactions to form cations. And so the hydrogen abstraction to form a secondary radical that goes over a lower energy hill. And so it's going to happen faster. Okay? This is going to happen faster because it's a lower energy hill. The one over the higher energy hill will take more time because it's taking more energy. But for chlorination, there's not that much difference because chlorination, remember the energy hill isn't so high anyway. And so there's enough energy in the system for it to get over both of those pretty easily. And so what happens, even though there's a 3-to-1 ratio statistically, 3 CH bonds, 6 CH bonds when you consider both methyls, and 2 CH bonds, that gives you a 3-to-1. But what you see is not just a statistical effect, because this is 60% to 40%. If it were purely statistical, it would be 3 times as much of this to 1 times that. So it would be 75-25. But it's not a statistical thing. That is the influence of this being, this secondary radical being more stable. That's what is making this be 60% and 40%. Okay? So, but it's surprising that it's only 60 to 40. Okay, so there's 2 things influencing that. One is the statistical effect of having 6 primary CH bonds and only 2 secondary CH bonds. And the other one is the stability of the secondary radical versus the stability of the primary radical. So 2 things are influencing this. And obviously the stability of the radical has a much greater effect. Okay? So that's what you're seeing here. Now with bromination, it's the opposite. Much, much, much more of the bromination at the secondary position, 97%, only 3% at the primary. So the bromination is much more selective. Chlorination is much less selective. Okay, and what we're going to look at now is why. Why? Bromination is much slower, so why? Here, this is chlorination again. Okay, this is what you just saw a minute ago. This is chlorination, where you go over a relatively small energy hill and you go down to the intermediates. This is chlorination. Okay, chlorination. This is bromination. And look here, you go up this huge energy hill and down to intermediates. And so the fact that this energy hill is so much higher, this makes it the opposite. This is very, very selective. This is not very selective. Relatively, this is much more selective. Bromination is much more selective than chlorination is. Okay? And also remember the little theory that we learned earlier, that whatever the transition state is closer to, that means it resembles that structurally more. So the transition state, since it's closer in energy to the reactants than it is to the intermediates, closer energetically, it will also be closer structurally. Over here, look at bromination. It's closer energetically to the intermediates. The transition state is closer energetically to the intermediates than it is to the reactants, okay? And so that means that the transition state will also be closer structurally to the intermediates, okay? The bromination transition state resembles the products. Here, the chlorination transition state resembles the reactants, okay? So here's another diagram pointing that out. So when you have the reactant come in, Cl dot is coming in, and it's just abstracting H dot, and so it will be much closer to the reactants structurally. So this bond will still be predominantly formed. Over here, this is much closer to the intermediates, and so when Br dot comes in to abstract H dot, this bond will be mostly broken, okay? So this bond will still be relatively intact over here, and over here, the bond will be mostly broken because this is closer to the intermediates, and this one is closer to the reactants. So that's what that means by closer structurally to the reactants, closer structurally to the intermediates. The bond is mostly formed, the CH bond. Here the CH bond is mostly broken. And so here, it doesn't depend so much, in chlorination, it doesn't depend so much on the stability of the radical that's being formed, and so that makes the stability of the radical that's being formed have less impact, less effect on the regioselectivity. But up here, since this greatly resembles the intermediates, the stability of the intermediate that's being formed greatly determines the product formation, and that influences the regioselectivity. So here we have another way of looking at this. So if you have a molecule where you can have a primary radical, secondary radical, and tertiary radical formed, here is what you're going to see in chlorination. The transition states are all very close to each other in energy, even though the products may be farther apart in energy. And so for chlorination, it's going to be more likely that you're going to get a spread of products. You're not going to get selectivity. So this is what is meant by saying that if it's if your reaction is very reactive, and here this is, that means that there's not much of a spread energetically in the transition state, then you're not going to have much selectivity. That means you're going to have a good distribution among these products. However, over here, energetically, we have, this is bromination. Here you see the bromine. There's chlorine over there. So chlorination, bromination. Here you see a good spread in the transition states leading to the products. And so that means it's going to be relatively easy to get over the transition state structure, the energy hill, to go to a tertiary radical. but it's going to be much harder to get to over the transition state structure that leads to a secondary radical, and even harder to get over the energy hill that leads to a primary radical. And so that makes this reaction much more selective. That makes it much more selective. It just barely has enough energy to get over this lowest energy hill because it's going uphill in energy. So the system just barely has enough energy to get over this lowest energy hill to get to the tertiary radical. And so that makes it much more selective. Everything is downhill, so it just blasts over all three of the energy hills. It has enough energy to attain any of them, any of those energy hills, and get over any of them. So it has to do with how much energy is in the system. So here, for chlorination versus bromination, here we have this is 2-methylpropane. So for chlorination versus bromination, you're going to have 9 primary CH bonds versus 1 tertiary CH bond. And for chlorination, it's about 1 to 2, okay, which shows that there is some selectivity. There is some regioselectivity. It's there, okay, because remember, there's 9 times as many of these bonds as there, okay? And so definitely there's some regioselectivity that's due to the greater stability of the tertiary radical. But look down here. For bromination, this is a much lower energy process. It just doesn't have enough energy to get over both of those energy hills. So it's just barely got enough energy to eke over the energy hill that's required to get bromination at this tertiary position. And so you get exclusively bromination at the tertiary position. So that explains the regioselectivity. And here, bromination, this happens 16 times more often than that. So there's a little bit of this, but it's essentially 0. And here, this shows the relative selectivity for bromination at the primary position versus secondary position versus tertiary position. So bromination is much more selective than chlorination. And for fluorination, it's almost indiscriminate. Remember, I told you that fluorine is so high energy, it just more or less reacts with the first thing it bumps into. So it has almost no effect, the stabilities of the intermediates, the radical centers. It just almost reacts with the first thing it bumps into. It's because it's such a high energy process. So that leads us to the stereochemistry. So note here, when one replaces the CH bond here, you do have a new chirality center formed. And of course, you're going to get chlorination at the primary carbon as well. With the 2-chlorobutane, this is a new chirality center. And since the radical that's formed at that position is almost planar, and you should consider it to be planar, and that means that you're not going to generate any chirality. You're going to have a racemic mixture there. It's going to be a 50-50 mixture. This explains why. You can consider it to be sp2 hybridized, or you can consider it to be a shallow pyramid, which is rapidly inverting. And either way, it doesn't matter which way you consider it, you're not going to have any stereochemistry retained. So, for example, here, that means that chlorination at that position, chlorination, you're going to get 2 positions. You're going to get some 2-chlorobutane and some 1-chlorobutane. This is going to be a racemic mixture, so you're actually going to have 3 different products present. And so the same thing here. Even if you have a methyl group there, you're going to, if this is S3-methyl hexane, you're going to lose your chirality. Okay, this is going to be a racemic mixture as your product. And so you're going to get bromination exclusively here because this is a tertiary radical that will be formed there. So you'll get bromination exclusively there. Okay, so that finishes our halogenation of alkanes, and we'll go on to some more specialized topics in the next section.